Hello, my name is Jiří and I'm a fresh PhD student at the Charles University in Prague. My supervisor is Pavel Pecina, and I'm going to be presenting a paper that tries to outline some of the challenges to be faced when we build our synthesizer for handwritten music. So let's first talk about synthetic training images. We all know that modern machine learning methods require lots of training data, and manually annotating this data is very expensive. And this is further complicated by the fact that there is not a single annotation format that we could use to label the data. The previous presentation about the data set showed that like can do something, but it cannot do other things, and the differences are there, and it's difficult to combine various data sets. So we don't have enough data. One problem to tackle this, as was said in the keynote, is to generate synthetic training data, where the advantage is that we have the annotations perfectly for relatively for free, because we need to annotation to begin with to even generate the synthetic image. So we tried to do this. We created a prototype synthesizer called Pecina that's freely available on the internet. Image synthesis in printed music is not new, because there are many datasets like Primus and Deep Scores and many others that contain music images of printed music, and these have been created using some engraving tools such as Verovia or MuseScore or Lillipond. But our synthesizer is different in that it tries to synthesize handwritten music images. So here's an example. At the top, we see a real-world image taken from the CVC Muscema dataset. And at the bottom, there are 6 images produced by our synthesizer, each in the style of a different writer. These writers are taken from the CVC Muscema dataset, the styles. And the last image is interesting because it combines the style of all the available writers. So the synthesizer works by taking an encoding of the music to be synthesized. This encoding is a custom one, and it can represent monophonic music. It parses this encoding, and somehow, we will see later how, produces the resulting image, which is technically grayscale. It's about 350 pixels tall, or more specifically, it's exactly 12 stuff spaces high, and this is set in such a way that the stuff lines in the middle take up exactly 1/3 of the height of the image. But since our encoding is non-standard, we also created a converter that can take the Primus agnostic encoding and turn it into ours. So now, how does our synthesizer work under the hood? First, before any synthesis begins, we have to create the so-called symbol repository. So for that, we take the Muscema++ dataset, which is a subset of the CVC Muscema dataset, and we extract all the images of individual symbols there. Then when we want to synthesize some music, we first need to get the annotation of the music somehow. So let's take a look at the annotation on the slide. When the synthesizer gets this annotation, it first parses it into groups of tokens. These usually have a note in the middle and some ornaments around it. And these groups are then parsed into so-called canvas items. And we will focus on the middle one that represents a quarter note with 1 sharp and 1 duration dot. So in order to render this canvas item, we will need 3 symbols. So we will go back to the symbol repository and randomly sample 1 symbol for, or 1 image for each of the symbols. now that we have the images, we assemble them together in the proper location. This is done by some handcrafted rules, and this will form the assembled canvas item. And we do this for all the other canvas items, and then we place them onto an empty stuff from left to right with some variable padding added in between them. And that's how the final image is produced. Now, what's difficult about this way of synthesizing images? Well, the synthesis can be understood as having two parts. First part is the symbol synthesis, which in our case is really simple because we just take all the images that we can and randomly sample from them via a uniform distribution for each occurrence of each symbol. And the second part is the layout synthesis, which is the set of all rules that somehow define how the symbols are going to be placed with respect to each other. The symbol synthesis is simple for most symbols, but there are symbols such as slurs and beams that can't be synthesized this way because we need them to have a specific shape depending on the music surrounding them. So we decided to render slurs as parabolic arcs and beams as straight lines, which is the simplest solution we could try, and it doesn't really model the real world because the real world handwritten slurs are not ideal parabolic arcs, and you can see on the image on the right, the beam here is even broken in half, so that's a feature that we cannot do right now. If I'm gonna focus on the layout synthesis for a while now, that problem of positioning symbols relative to each other is currently solved by lots of handcrafted decisions in the source code of the synthesizer. And to give you an idea of what I mean, let's take an example of determining whether a stem for a note should be pointing up or down. It's a simple yes/no question. This question seems simple. If we have a note that should be positioned lower on the staff, the stem should typically point up. And if the symbol is high on the staff, it should be positioned down. That's easy. That's what we do in our synthesizer. But if we want to extend the synthesizer in the future, the music is way more complicated than this. So for example, this note is pointing up because there's a second voice underneath it, and they can't both be pointing down because they would collide. This is what happens when the two voices have the same pitch. They actually share a single note head, so suddenly one note head disappears. So we could say that the note head has two stems, which kind of breaks our framework of looking at the problem. And this note is pointing down because it's actually an eighth note in a piano form. So there are lots of and these decisions are everywhere in the synthesizer. Like for example, if you want to place a duration dot, you should be careful because usually duration dots are placed in stuff spaces, because if you place them on stuff line, they aren't readable. And the same thing happens with positioning accidentals and so on. So in the future, we would like to first improve the system for synthesizing lines in general. These are beams, slurs, but also stems. Currently, stems can be just sampled, but it would be better if we could use the same system to synthesize all three of these simple classes. And for the layout synthesis, we would ideally like to learn the layout rules instead of handcrafting them, because currently the synthesizer is relatively small, so the handcrafted rules are manageable. They can't easily be changed, that's one thing, they are not flexible. But the other thing is that if we want to add more features into the synthesizer, they're going to interact with all the existing rules that are already in the synthesizer, and managing the complex code base is going to be really difficult and costly. At the end, I would like to list some limitations of our prototype. as I mentioned in the beginning, it currently can only synthesize monophonic music. It's limited to symbols from the Mistima++ dataset. This could be extended in the future because we have plenty of datasets containing musical symbols. We currently work with non-aligned annotations, but some models require aligned annotations. In the keynote at the beginning, there was a description of the frame-based labels. That's an example of an aligned annotation. And also we use a non-standard input encoding. So our plan for the future is to provide multiple encodings, either as an input and or as an output, so that the data can be used in multiple situations. And also our current pipeline does not perform any post-processing. So we synthesize the perfect image with no distortion, with no blur or paper degradation. It's something that could be added on top. So to summarize, we think that synthetic data will be important for handwritten recognition. And the synthesizer does not need to be perfect to be useful, because our synthesizer, we've used it to achieve quite surprising performance, given that we've trained just on the synthetic data. I haven't included any examples in the slides, but we can discuss it later during the panel. And the primary challenge, we think, is to somehow handcraft as little rules as possible, and to ideally learn as many of them from some data sets such as Mistima++, so that the synthesizer is simple and can learn various writer styles easily. So that's all from me, and I thank you for your attention.
Yeah, thanks. That was really interesting. I was wondering if the output from the synthesizer is deterministic, or if it's you have random variables baked into it so that it's slightly different each time.
Well, yeah, currently, if I go to the slide where we assemble the canvas item, like as a single example, we take the individual image. Well, first variable is sampling the symbol repository, and we can constrain the repository to a subset of writers. That's how we achieve the various styles if we want to do that. But when we compose these images to their respective position within the canvas item, there is a fixed vector, like from the center of the node head to the accidental where the accidental should be, plus then there is some uniform interval that we sample, and we add this variation into the position, so it can actually sample. Like, for example, here in the final synthesized image, you can see that the accidental, the sharp is actually almost one position above where it should be. So that's the variable that is introduced, and that changes every time you sample from the synthesizer. And similar randomness is added like in most places where position is somehow calculated.
Mm-hmm.
But it's fixed for all the writers. Yeah.
Right, but it's one of these things where, like, if you seeded the random number generator, I assume this is in Python, right? So if you seed it first, Python, then you should get consistent results. But then you can play with a random number seed to get different things.
Exactly.
Yeah. Okay. Mm-hmm. Cool.
Other questions? Maybe from my side, one quick question here. You mentioned it briefly, but do you have plans on expanding this to polyphony? And if yes, how?
Well, actually, the synthesizer, most of it was produced like 2 years ago when I was writing my bachelor thesis. And then for my diploma thesis, I did something slightly different. So it was like sitting on the shelf. And now for my PhD thesis, I'm getting back into it because I realized that like the semi-supervised learning that I did for diploma thesis is not really gonna cut it. So I'm going back to synthetic data, and that's one of the plans for the future, to extend it to polyphonic music, because now I have the understanding of how actually polyphonic music works, how multiple voices interact on the score. I looked at the source code of some of the engraving systems, such as MuseScore. So now I know that the way I've designed the synthesizer is actually quite similar to the way MuseScore actually engraves a stuff.